Okay, good morning. Let's get started. Can you hear me in the back as you're walking in? Sounds okay? Okay. Today we're going to continue the journey. I think we left off in a nice place last time, talking about the basic classical machine learning ideas, ideas around machine learning. Today, we'll pick up where we left off and really talk about this new thing, relatively new thing, called deep learning. And along the way, just kind of fill in the gaps, because I think the real fascinating thing that maybe you might not know, if you've taken deep learning before, you might know the ideas. But what's really fascinating to me is how we got here. And GPUs have a really strong place in helping us get to where we are today. And I want to tell you about that story because it's incredibly fascinating. A lot of pieces came together in the recent past, within the last 20, 30 years, actually within the last 10 years, to bring us to what I think is a pretty pivotal point in the technology history. I'm going to say a message that I said last time, which is there's a lot of stuff for all of us to pay attention to. Cryptocurrency, metaverse, deep learning, autonomous vehicles, robots, blah, 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 blah. I really think deep learning in that spectrum of things is very real. And I know that because of my interactions in the commercial sector, and I know how effective it is. It's incredibly effective. So it's important for us to understand it. And really over the last lecture and this lecture and the lecture next time, I'm hoping I can give you a little bit of that perspective on what's real, why it works, and how to go a little further if you're interested. Okay. Hopefully I can get this screen to work, and we will get started. There we go. Okay, before we start, just a few reminders. Labs, all of them will be graded by end of this week, so up to lab 4. We want to make sure you have all the labs available to you as you get ready for the upcoming midterm, which is October 11th, Tuesday. Now, a note on the labs, okay? The grades are trickling out. By and large, they're correct. If for some reason you got a 0 and you're pretty sure you shouldn't have gotten a 0, get in touch with one of the TAs. You don't have to put a note on Campus Wire, okay, because it's sometimes, rather what you can do is you can send an email directly, and we'll try to get it resolved for you. Okay, there's some students whose grades have fallen through the cracks for one reason or another. It's legitimate to be concerned if you feel like the grade you got is not the grade you deserve. Feel free to reach out. Okay. Midterm 1 is on Tuesday, October 11th. It's coming up. It's 2 weeks. Yeah, 2 weeks from today. Again, it's online. Everybody will be taking it at the same time, which is Tuesday, October 11th, 7 p.m. to 8:20 p.m. U.S. Central Time. And then if you're taking it in Beijing, which none of you are, in Zhejiang, Haining, which is the ZJUI campus, it's 8 a.m. to 9:20 a.m. Local time. So everybody globally takes it at the same time. And it's an hour and 20 minutes because that's the class slot for the students at the ZJUI campus. Okay, everything is calibrated to be an hour and 20 minutes. The materials go from lecture 1 through lecture 10, which is right up until the end of the convolution lecture. Okay, if you have a legitimate reason to take the conflict, that is, you cannot make that time because you have another exam, you have another course that is mandatory, and we'll check, then we will offer a conflict, okay? But it's got to be a very legitimate reason. And, you know, things like, well, my friends and I have a thing going on that night. That's not a legitimate reason. Clearly, you know that. Okay? Please let us know by this Friday so that we can make appropriate plans. Last thing, we are starting the project officially on Thursday. Okay, so we're going to release some information about that. And the baseline CPU version of that project will be due 2 weeks from Friday. Okay, and it's pretty straightforward. It's we're going to talk a lot more about it over this lecture and next lecture, but it's just the CPU code, which should be pretty straightforward for everybody. Okay, any comments, questions, feedback before we start?
If it's just a CPU implementation, will we be able to run it locally even without an NVIDIA GPU? Or do we
Yeah, no, you can run it locally. We might be asking for profiling information, in which case, just to keep apples to apples, you'll use Rye to submit it, collect the data, and then you'll get your results. Okay, but you can test it out on whatever you want. Okay, but it's just C++ code, so it should run pretty much anywhere. Okay? All right, great. Let's just jump into it. Where we ended up last time was we were introducing a basic atomic piece of this whole machine learning, deep learning paradigm. This idea of a perceptron. Okay? Like I said, leading up to the perceptron, there's like half a dozen ideas in the machine learning world. Linear regression, support vector machines, so on and so forth. There's a bunch of ideas, and of all those ideas, and by the way, we call this set of ideas classical machine learning. And they've been around for quite a while, and I would say moderately effective. You could build a classical approach, given enough data, to, let's say, get to 80% accuracy on some task. Like, let's say, predicting whether somebody would click on a particular content on a website. Like, this video, are you going to click on that video or not? Maybe you can get to 80% accuracy on that with classical approaches. Or maybe saying, does this image have a cat or a dog or a bird or a boat? 80%. Now, I would say that the classical approaches, for most purposes, never got to good enough to say that, these are better than we can do with a human. Okay. But deep learning kind of crossed that chasm from being like, oh, that's pretty interesting, to, wow, this is good enough to put on a massive scale for whatever problem it is that we're trying to solve. To get to the deep learning piece, we need to talk about a classical machine learning piece called the perceptron. Okay, the idea behind a perceptron is, again, it was biologically inspired because, well, we kind of understood how this thing worked, a neuron, And the idea behind the neuron is, well, we've got some set of inputs, or at least the idea behind the perceptron, is that we've got some set of inputs, x1 through xn, that we're going to linearly combine. And by linearly combine, now all I'm saying is I'm going to just multiply each input by some weight, w1 through wn, and then add them together. And I'll add some scalar bias to that to generate the effective output of that perceptron. Okay? If we just have a one-dimensional input, all we're doing is we're creating a line. Right? It's just a linear equation. This is just a linear model. If I take a look at this output right there, which is just a linear combination of the inputs. That's all it is. We can do that in our heads, even if it's an n-dimensional input. Now we add something interesting to the end. We will call that the activation function. And we're going to talk about various activation functions as we go through this. But in the classical sense of the perceptron, the activation function here is just the sign. If it's positive, if it's zero or positive, if it's positive, the output of the sign function will be 1. If it's 0 or negative, the output of the sign function depends on the implementation, but let's say it's 0. So it's either 0 or 1. It's a binary output based on this linear function on the input. Okay? That's the idea of the perceptron. And if we take that and we kind of represent it in a linear algebraic way, we've got a vector of inputs, x1 through xn. So x is a vector in a general form. And we're essentially doing a dot product with the weights. So it's a vector dot vector. So we get a scalar value there, just one number. We add a bias to it. And then we run it through the activation function. Okay. That's the starting point. Even if we take a look at today's deep networks, somewhere in there, they will often have a perceptron or some set of perceptrons. Kind of everything builds on this notion. Okay? Now, it's pretty simple. And what we're going to do is we're going to start to assemble these things together. That's what I showed you on the previous slide. It's just x1, x2, x0, x1, x2, linearly combined to produce y on the output. Okay, single perceptron right there. And as I said, input vector dot dot weight vector should be a dot, not a multiply. In order to compute plus the bias to produce the output. Now what we can do is we can start to array these things together to create, for example, a fully connected network. So I've just got, in this case, 4 perceptrons, each calculating an independent output, or 5 perceptrons, each calculating an independent output. Y0, Y1, Y2, and so forth. Okay, so just generalizing slightly by saying, I can take one, array them together, where each one is fully connected to the input layer to create something a little more sophisticated. Where each one of these is just a linear function with an activation attached to it. I mean, at this point, it just seems like some mathematical concept, right? The interesting bit is that, well, we're going to learn the weights. And once we learn the weights, and we add a few more things to it, these things become what we're going to say is a generalized function. And we can learn these things to do certain tasks if we can have some examples. We'll get to it. Okay, any questions so far? Well, let's keep going. All I'm doing is I'm just adding more layers. I'm sorry, I flipped the chart here, so it's no longer going horizontally, but now we're going vertically. So I've got the inputs at the top, and I've got layers of perceptron. And then I've got this stuff here, I'll get to it in a second. But those circles are just either the input layer, or the hidden layer, or the output layer. And I can have as many hidden layers as I want. And one of the things that I think is confusing and kind of troubling about deep learning is, as a student, you really need to keep all the terminology straight, and the subscripts and this and that and the indices. And I find that a lot of young students just don't have the patience to battle through all this. And rightfully, I mean, it's just details, right? But it's easy to get confused on those details. So, by and large, in this class, we're not going to worry about those details. We're going to talk a little bit at the high level. But it's important that you give yourself a chance and you try to weed through these details. So let's just try for a bit. So we've got some input. It's a multi-dimensional input, meaning I don't have one input, I've got n inputs. Okay, so we're going to generally talk about the inputs as x. X are the inputs, but it's a multi-dimensional, in this case, input of size 4. Okay, now that input layer, it's just the inputs. There's no perceptrons per se at the input. Those inputs go into the first hidden layer. Okay, and in that first hidden layer, they get combined according to the rules of the perceptron, right? So this is essentially an array of perceptrons. I've got 4 of them in this case. I can have as many as I want. 10, 15, 6, 3. It's independent of the number of inputs, really. Each perceptron, because it's fully connected, is going to take all the inputs into consideration. How do I choose 3, 4, 15, 6? It depends on what I'm doing. And that's part of the art of building a deep network. Part of the architecture of the network, which is part of the innovation around the network. It depends on what we're trying to do. Okay, so these hidden layers combine, and again, they themselves can go into another layer. In this case, the output layer, where those perceptrons in the hidden layer are now combined together in the same way as any other perceptron. So each of these has how many inputs? Think about it in your head. It's just, well, how many ever outputs there were in the previous layer, right? The outputs of the previous layer all become inputs of the next layer. And finally, we reach the output layer, where we've got some number of outputs, in this case, 3. The output layer now starts to correspond to what it is we're trying to accomplish. Here it's generic, we don't know what we're trying to accomplish. But in a few minutes, I'll show you a real network where we're trying to accomplish digit recognition. Okay, so digits 0 through 9. So the output layer, just through logic, right, would have 10 outputs, 10 digits. Yeah, and maybe you're thinking, well, what if it's not a digit? So maybe we can have 11 outputs where it's 0 through 9 and not a digit. That's another way to do it. But again, that's our decision. Yes, question?
This might be semantics, but when we talk about the layers, are the layers themselves the data in between two sets of nodes? So like it would be Z0, Z1, Z2 for like the output layers, that's the third layer of nodes of Perceptrons.
Think about a layer as the input coming in from the previous layer and the output going to the next layer. So it's everything in the middle. It would include the perceptron, the activation function, and any other functions that might be included in that layer. Okay. Now, so we've got this output layer, and sometimes, depending on the task, we might include kind of a remapping layer. Okay, so these are, let's call these Z's some real value. Okay, so, these perceptrons here, I guess if I'm using the sine output, they're just generating binary values, right? Because if I've got the sine activation on these perceptrons, well, depending on whether they're positive or 0 or negative, I've got whatever value that I'm going to get. Now, what we might want to do here is apply some kind of remapping to take those and map them to whatever it is we're trying to accomplish. For example, if these are not binary values, but rather real values, as I'm going to show you in the next example, what I want to do is maybe convert them into probabilities. So I'm going to remap it into something that takes real values, computes probabilities, so that now I have a probability that says, well, it's either K0, K1, or K2. It's going to be useful when we talk about digit recognition, because I want to be able to remap into probabilities so I know which digit has the highest probability for being the output. Okay, now, as we go through this, what is really important that I want you to keep in mind is that we're going to try to map all of this into a linear algebraic framework so we can use the power of linear algebra, convolutions, matrix multiply, vector dot product, dot, 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 onto this. Because quickly it's going to go from 3 inputs, 4 hidden layers, 3 outputs, to something much more massive. We can't sit there and do things by hand. We got to put it into a framework like linear algebra. There was a question, yes?
Yeah, I'm wondering why the dimension of the W2 is 4 times 3. I think it's probably 3 times 4, so that we can get a vector.
Oh, let's see. Maybe there is a mistake there. Let's see. So, so you're saying it should be 3 times 4 instead of 4 times 3? Okay, let's see. The weight matrices entry ij is a weight between input I and output j. So I is the input and j is the output, right? So here we've got 3 nodes, 3 outputs. So j is 3. But we've got 1, 2, 3, 4 inputs, right? So each weight, there should be 4 weights for each of these nodes. So it should be 4 times 3, 4 by 3.
But for me, it's just like multiply the W with 4 times 1 vector. So if we have like 4 times 3 times 4 times 1 vector, it doesn't.
No. What we're going to do is we're going to take each row in W and multiply it by the input vector. Okay, so we've got 3 rows, row 1, row 2, row 3 for the weights. Yeah. Any other question? Yeah.
I think both either way, it works depending on how you set up the matrix multiplication.
Yeah, it is. Yeah, you can transpose, yeah, of course. But we need 12 weights. Right? That's the idea. We need 12 weights in order to fulfill the idea here. Okay, so let's move on to something concrete. Okay, let's say we want to build a digit recognizer. So handwritten digit, and they're only digits, let's say. It's got to be one of 10 things. The 11th thing, it's not a digit, not here. Everything has a digit, just to keep it simple. So I've got 28 by 28 input. It's a little image of the digit, grayscale. So it's each input, think about it as a value between 0 and 255, grayscale image. And what we want to do is produce on the output, like at the output, a probability that it's either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I see the probabilities, then I will select the max probability as the output. Okay. And we have plenty of labeled images. We've got, this thing called MNIST out there. You can easily download it. I'm sure if you've taken a machine learning class, you've already done this. This is like machine learning MP Lab 1. Okay, so they're there. Well, how does this network work? And yeah, people have studied this thing all over the world. And a multi-layer perceptron does very well at this. We don't need to go deep. MLP, multi-layer perceptron, is very good. You get high 90s in terms of accuracy. But it's simple enough for us to discuss in class. Okay, so there's the input. 784 pixels. So my input, if I just vectorize this image, by the way, when I first learned about image processing and computer vision, it always puzzled me that, oh yeah, why you're just taking this input and treating it as just a big vector. Seems convenient. But aren't we losing something in that process? We are, and we're going to get to that. But it was very convenient, especially if we talk about things in an MLP framework. Why do I say we're losing something when we do that? Yeah? Yes, very good. If I'm taking this thing and representing as a single dimensional vector, I don't know how the columns relate to each other. I know how the rows, data within a row, relates to each other because the rows, by and large, are preserved. But if I have something in the column dimension, it's kind of lost, interspersed through this data. I have to relearn that, which adds a little bit of complexity. We'll get back to that. Okay, let's not worry about it right now. So 784 inputs go into the hidden layer. This architecture here, by the way, is just one hidden layer. Probably if you had 2 hidden layers, might be more accurate, but that just would make for a complex diagram on this PowerPoint slide. So I've got here 10 hidden layers, or 10 nodes in that layer there. Okay. And each one is a perceptron, taking in how many inputs? It's fully connected, so 784. So each of these has 784 weights. How many biases? How many biases? Yeah. Sorry? Per node. One. One per node. One bias, 784 weights. So the weights, by and large, are kind of the more computationally heavy item in each node. And I've got 10 nodes. So I've got 7,840 weights. Already the system size is looking pretty substantial. And 10 biases. Okay. Yeah, and that's what's happening, right? It's this function that we're computing for every image that comes in. And then we take that layer and we propagate it to the next layer where each node is now responsible for calculating the probability of digit 0, digit 1, digit 2, digit 9. Okay? In fact, we'll get to those, the specifics there. So if I kind of sum it all up, I've got all those weights, all those biases that I don't know what their values are, right? I can't sit down with a piece of paper and write down those 7,840 weights or even those 10 biases. That would be, I don't think a person could do that, or even a team of people could do that. But algorithmically, we can determine those. Right, so what we say is, and then if we include all the weights and biases here, what we say is this whole network has 7,960 parameters. That's a little important idea there, that we have to go learn those things in order for this thing to be effective. Okay. And if we're talking about like a modern deep network, like the ones that make the news kind of networks, like the deep foundational language models, which we'll talk about at some point, they've got billions of parameters. So you need lots of data and lots of computing power in order for those networks to get trained. Okay? Any questions on this? Yeah.
So for the third layer, it's like can just complicated ways.
You mean this layer here? Yeah. Sure, it could, but it could also have a perceptron, meaning it could have a set of weights there, and often it will have a set of weights there, okay? Because the advantage of these layers, we're going to see it. I'm going to show you pictures of what these weights look like in a moment, okay? That combination here is going to be really important. So having those weights there is going to matter. Okay, but we also need to kind of calculate the probability, so we've got things like the softmax in there. We've got something like an argmax in there to find the thing that's got the highest probability. But those are all simple things at the output to calculate, okay, is it a digit? Which digit is it? Okay, let's move on. By the way, any other questions before we move on? Okay. So the magic of any of this is really, how do we determine weights? Okay, let me give you a quick historical perspective. We are like in the 1960s and 70s right now. And we're talking about one hidden layer, maybe two hidden layers. 8,000 parameters, maybe 15,000 parameters. Because that's all we could do. We didn't have like all the pieces in place to really do anything more sophisticated. We didn't have the computing power to do anything more sophisticated at the time. But we also didn't really know how to learn across many layers. If we picked one node, let's say we picked one node. Okay, so what is one node? It is a linear function. How do we learn if you had to do it by hand and I gave you a bunch of data? What is that one node doing? You all know it. I think you all know what that process is. And I'm not talking about backpropagation. I'm talking about something else that you learned maybe even long ago. I give you a bunch of data. What is that one node? How do you take that data and find the weights for that one node? What is that process? Yeah? Trial and error. Yeah. Probably as a kid you would have tried trial and error. But how do you know if a trial is good or not? Yeah?
So are you talking about loss function when you compare your prediction with?
Yeah, you didn't learn loss function long ago, right? You just learned it, right? Least squares line fitting, right? That's all that process is, right? I've got a bunch of data. I'm trying to draw a line through it. That's how we did it by hand. And you, no doubt, have done it by hand. We can do it by hand for one node, provided that one node isn't too high dimensional, meaning like less than 3. So what I just said, right? I've got a bunch of, I draw a bunch of dots on a piece of paper, and you draw a line through it. That's the trial and error he's talking about. But we can measure how good that line is by doing something called least squares. Okay, here's a better line. Here's a better line. And I know because I can calculate the least square. The least squares figure on it, right? Well, let's take that idea and let's build it out algorithmically so that we can handle 784 inputs and just not 2. And let's do it so that we've got 10 and just not 1, and dot, 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 dot. Everything I'm going to tell you about is just that idea. It is that idea. And that's the magic of even deep learning. Does that make sense? Okay. So let's move on. And it's really about, I've got roughly 8,000 parameters. I don't know what they are. And I want to go figure them out. Okay. Those are all the things I do not know. And that's just the first layer. I've got an output layer also. Okay, so the idea is simple. What we are trying to do is we're trying to approximate the input-output function. I've got x, that's the input. I've got y, that's the output. And I've got a function that I'm representing as a perceptron, or a set of fully connected perceptrons. And I'm trying to figure out how to match that perceptron function to the function that is the thing in reality that I don't know. So the breakthrough here is this. And this is what somebody was trying to get at, which is, well, we know how to do the forward pass. So if I gave you all the weights and all the biases, well, the inference is easy. I take the x, I know what all the weights are. I know what all the biases are. And I calculate the output, right? That's called the forward pass. Yeah, it's compute intensive. And we'll see some very compute intensive forward passes before we finish up. But the forward pass, pretty straightforward, right? Any questions about the forward pass? I would hope not. That's just algebra, linear algebra at that. What is the breakthrough? Is this idea of backpropagation. Okay, and that this is essentially one of the things that helped us go from simple networks to very complex deep networks. One of the pieces. All right, and it was originated by Rummel, Hart, Hinton, and Williams back in 1986, so it's not that new. But it really enabled us to be able to train networks that have many layers. And the idea is, I need an error function, E. It's like our linear least squares function, right? Somebody said, well, trial and error. I draw a bunch of points on a line, on a piece of paper. I draw one line, and I draw another line. How do I know which line is a better line that represents that data? Well, I can calculate a error function, which is the least squares metric on each of those lines. All right? So in general, if I have an error function, E, what I can do is do the following. I pick parameters, which I'm going to say is theta, which is really the weights and the biases. I calculate the error for those weights and biases, right? Picking the weights and biases is like picking a line on those set of points that I put on the paper. That's all that weights and biases are. Now, given a line, I can calculate the least squares of that line. That's what E is in a generalized sense. Once I know E, what I can do is then adjust the weights and biases to reduce E. And I keep doing this over and over and over again. Okay? And that's the idea of backpropagation. I'm going to throw a little calculus in there. You're going to see that in a moment, because I need to know how to adjust theta in order to reduce E. So what I'm going to do, just to throw some calculus in there, is I'm going to say, well, E is some function in some very high-level, highly dimensional space, and it's a smooth function. So that is, if I'm at any point, I know the gradients around that point. And what I'm going to try to do is go down, because I want to reduce E. So I need to know what the gradients are. Gradients are partial derivatives with respect to all the dimensions. And I'm trying to reduce E, and by knowing which direction to take it, I can adjust theta. We'll go into the details. Okay. That is the high-level concept. That came in 1986, right? Perceptrons around 60s and 70s, 1986, whoa. Now we can start to train these things, and we can add many, many layers. Questions? Yes?
What's the point of all these layers?
What do the layers do? That's a funny question. It's a good question. The right question. But I think we don't yet even have great answers to that. Let's suffice it to say that what we're trying to do is we're trying to approximate a very complex function in the real world. And we're trying to compute that very complex function with a combination of linear functions that are assembled together to get that complexity. Okay, kind of, in my own words, kind of taking piecewise linearizations of that complex function. And those linearizations come from the various layers. I'm sure that's not the right way to say it, but let's just say that's right. Okay? Okay. So, I want to talk a bit. So we're here. I want to talk a bit about what we're going to call the activation function. Let me cross this word out and just let me use activation. And just to remind you, example is the sign that we threw in there. And it turns out that these activation functions are critical to the performance of a deep network. In fact, his question was a great one, right? We can understand an individual perceptron. We can even understand that, okay, I've got a bunch of them in a layer. The idea of piecewise assembling them to model a very complex, many-dimensional function is really kind of, it's kind of the right mental model. And these activation functions serve as ways to assemble them in nonlinear ways. Okay? So they're important. And the simplest version is the sign. And in this case, if I drew the sign, and this is what the sign looks like in the case of a perceptron. So it's -1 if the value is 0 or negative, and 1 if it's a positive. Okay. What we want is something that's smooth, because we want to differentiate it, right? I had mentioned that we want to be able to look at the slope to find which direction that we want to tweak the parameters in that backpropagation step. So we want functions that don't have discontinuities. They're differentiable. Okay? And we also want functions that are not flat. So a sine function is bad in all ways. It's got a great discontinuity, and it's flat, so there's no slope. And if I'm here somewhere deep in -500, it's hard for me to know which direction to move to try to increase the value of or decrease the value of the error function. So we don't like sine. Lots of choices here. And if you're a student of deep learning, you know that, you can use all kinds of functions. A popular one for a long time has been this idea of a sigmoid. And it's a good function to have in mind. It kind of comes out of classical machine learning. When people were working on things like logistic regression and linear regression, primarily logistic regression. It's a very nice function in the sense that it approaches 0 for negative values. So it doesn't go below 0, but asymptotically approaches 0. And asymptotically approaches 1. So it's a nice, kind of smooth version of the sine. And it's not flat, and it's differentiable. So, very nice function that we can differentiate, and if you want to work through the calculus, it's here. It's kind of easy to compute. It's very popular. Now, today, kind of the activation function that seems to be widely used in practice is the rectified linear unit, or the ReLU function. And if any of you have done machine learning before, you have heard the term ReLU. Okay. rectified linear unit. That's the idea of it. And it looks like this. If the value is negative, it's 0. The output is 0. If the value is positive, the value is x. So it's really the function f of x equals max of 0 comma x. If it's much faster, there's no exponentials. Unfortunately, it's still got a discontinuity and a flat slope. So smooth ReLU, you'll see it used in practice as well. It's just an approximation of ReLU that's smooth. And it's there. Also called the soft plus function. Lots of variations on these activation functions. They're very important. They're all parts of deep networks today. And again, they essentially take the perceptron and reposition the output in some way, or collapse the output in a nonlinear way. But very simply, okay? Any questions? Okay. Just one more thing to add to your repertoire, just so you know. What we might also do, and you saw me talk about this, is to say, well, I want to produce an output that is the probability of this being a 0, being a 1, being a 2, being a 9. But sigmoid and ReLU don't produce probabilities. They just produce, outputs that are what they are. So we will often use something like the softmax function, which you can see it here. It just takes the individual outputs and puts them into an exponential space in order to calculate probabilities. Okay, so the sum of all the k's that are coming out of the softmax sum to 1, and we can treat them as a probability. Okay, so it's again remapping. It's remapping from a bunch of outputs in the real space to something that's more akin to a probability. Okay, any questions? Let's talk about error function, if not. And we're going to assemble this together. I know that we're kind of deep in the weeds at the moment, okay? So, again, let's think about hand digit recognition, or digit recognition. So I put in an input, I put an image in. I know what the image is. I've got a label. I know what the answer should be, okay? So I know what the answer should be. What I can do is I can calculate an error that is E equals 1 minus KT. What is KT in this case? KT is let me just go back up here. Just going to go back to my perceptron. And we're going to say this is K0. This is K1. That's the probability of it being a 0, probability of it being a 1, probability of it being a 9. Okay, those are the outputs in this case. I'm going to call them K. So how do I calculate an error? I need an error function. And the error function is going to be important. We call it a loss function sometimes, actually often. You can also call it a gain function if we're trying to maximize it. Okay, but the loss function, in the simplest sense, could just be the probability of not classifying it as T. So I know what the answer is. So the answer is 3. So I know the answer, I know what K3 is. And then I'm going to calculate the error as linearly a function of the real probability. And that's the error I'm trying to minimize, right? That's a way of calculating it. Now, oftentimes what we want to do is kind of put a quadratic in there to kind of strengthen the position of the error, kind of like our least squares, right? You can see that this is starting to look like least squares. I'm trying to minimize the square of the error. So I can create an error function because I know the answer, t, and I know all the probabilities that the network is spitting out. And what I'm trying to do is force my network to pick the one that should have been picked. So I know what the error is given this input and given the output in the network. Again, if you're confused, go back to the dots we put on the paper and the line we drew through it. That's essentially the analog of that in the handwriting digit recognition. Okay, moving onward. I'm going to just briefly talk about the error determination, okay? We're not going to get into the details, but I just want you to understand it. So if I took and kind of wrote out the forward pass, again, algebraically, I've got x, which is my input. It's my 784 bits of pixels of input. I've got the first fully connected layer, FC1, which is just a bunch of weights times those pixels plus a bias going through the activation function. In this case, we're going to use a sigmoid. That all goes into the next layer, sigmoid, softmax, so on and so forth. I don't know which network this is, but let's just say that's the network. Okay? And then at the end, I've got some K, which is the softmax of the layer that came in before it, right? So this is a network, and I can describe it, the forward pass, is just an assemblage of those functions. I calculate an error, E, because I know the answer. I know what the answer should be, E. I know what the error is. What I'm trying to calculate is that gradient, which is, in this case, the partial derivative of E with respect to K, which is the layer that came in right before it. So what I'm going to do is I'm going to use the chain rule and, simple differential calculus to figure out what the various parameters at each layer, how to adjust them in order to minimize, in order to take one small step towards minimizing the error function. So let's put it at a higher level. I take some input x, I run it through. I know what the answer should have been because it's already been labeled. I look at the error, and what I try to do is, using my algebraic formulation of the network, I calculate the partial derivatives all the way through so that I'm taking a step towards minimizing the error. So, and then I adjust all the weights. Okay. Now, you can go through and you can figure out what the derivatives should be. We're not going to worry about that. Everything it turns out that today, regardless of how I build up my network, whether it's a network that looks like, algebraically up there, or it's something more complex, there's enough auto-differentiators out there that will automatically auto-differentiate your network and do that backward pass for you. So we don't have to get caught up in all the calculus. But it's important for us to realize what we're trying to do, right? Forward pass, easy. Backward pass, we're trying to update all the weights such that we're minimizing the error. Okay, so some details here. The point of this slide is just to say that we can put everything into a linear algebraic framework so that we're talking about the forward pass as matrix vector multiplies or vector dot products. That's all it is at the end of the day, along with all these nonlinear things, which are also very simple. And then the backward pass, although it looks complicated, right, we've got a lot of differentiation happening, it too is nothing more than linear algebra, once I know what the derivatives are. It's a lot of linear algebra. That's the thing I need you to keep in mind. Lots of lab 2 and lab 3. Okay? Now, let's pop up a level. Let's make this less mathy and come back to something a little more algorithmic. Okay, so here we are. We have a network. We figured out how to do the forward pass. We've written some code. Maybe we've used auto differentiation to figure out what the backward pass should be. Okay. And we also have a bunch of labeled data. So that is, all the X's and all the Y's, like the labels, like this is what the answer should be. Given this X, this is what it is. This is a picture, 28 by 28, and it's a 0. Here's a picture, it's a 6. Right? So we have all that. Now, what we apply to it is a pretty important step in the backpropagation world called gradient descent. It's just iterative application of backpropagation to start at a point, maybe a random point in this, highly dimensional space, and just kind of work our way to a point where we've minimized the error. Now, let's not say that we've globally minimized the error, because that would be luck. It's so highly dimensional that we don't even know where the global minimum is. A lot of local minima. But what we're trying to do is we're trying to pick a point. Maybe we pick it randomly. So 8,000 parameters, I pick 8,000 numbers, and there we are. I'm going to iterate through the training data to minimize it using backpropagation. And now I end up at a point. How do we do that? Well, the idea is, there's 3 ideas. And they're all very simple. The first one is batch gradient descent, or sometimes we just call it gradient descent. And what we do is, we take all of our input, X, we kind of batch them up. Okay, where these batches are kind of, they're randomly sampled, statistically equivalent batches. Maybe there's 5 batches, or maybe there's 100 batches, doesn't matter. And then for all the inputs in the batch, we do the forward pass for each input. We look at the error, and we backpropagate to try to figure out how to adjust each of the parameters. So we do that for one input. We do that for the next input. We do that for the third input. We do that for every input in a batch. And we accumulate the parameter updates. So that once we're done with that batch, we then adjust the weights and the biases. Those are the thetas. And we use this parameter here, epsilon, to kind of just adjust how much to really shift the theta. And that's called the learning rate. Okay. And that's all part of it. I'm going to zip ahead here. I'm kind of running out of time. There's also this idea of stochastic gradient descent. The problem with gradient descent is I'm running through all my input in order to do an iteration through the training input. Stochastic gradient descent says, don't use all the training input, use one input. Sample that input, run through the algorithm, adjust the parameters, and then do that a bunch of times. Okay, so it's far less computation than the batch gradient descent. But of course, we're not getting the robustness out of the batch gradient descent because we're just looking at one example instead of all the examples. Of course, we're going to do this a bunch of times, but the updates are based on one. And of course, there's a middle ground, mini batch, which is, okay, don't do all of the inputs and don't do just one of the inputs, but pick some set of inputs. Call that a mini batch. It's probably the more common way of doing things. Okay? And if I were to take a network like the one I showed, the multi-layer perceptron, and run through this process and just look over all of the training intervals, which we call epochs, what I would find is, hey, the network converges and really gets a very low loss, right? Let's say this is my loss function here. Let's simplistically say the loss function is how often I'm right. Okay, so my loss goes down, after a few training intervals, epochs. Great. It gets quite low. Awesome. But what I find is if I take that network and then I take it on and I put into it, something you scribble on a piece of paper, it doesn't do so well. That's that green line. Okay, the green line is, the blue line is on the training data. The green line is on everything else that's not the training data. So we often run into situations where the model doesn't generalize to input it hasn't seen before. So that's something we have to worry about. And some networks are better at this than others, but this is not uncommon. This is the thing that gets you the academic paper, and this is the thing that gets you deployed in the real world, right? Actually, the academic papers, just to be clear, are now focused on that as well. Okay. A bunch of stuff here. Now, if I were to take hand-digit recognition perceptron, multi-layer perceptron, and kind of put it to work and train it, what do these masks look like at the end of the day? So here's a little visualization just to give us a sense of it. This is the first layer, right? The layer that takes the input, we've trained it, lots of input data, and that's what we see. And then this is the second layer, and that's what we see. So here's where the interesting bits start to arrive, right? So this was not, there was no human in the loop. It was all algorithmic. The humans provided the answers, the examples and the answers. And the machine learned this. Perceptron 0 in that first layer, what do we see? We see what looks like a 0. You see the bright spots representing where the ink is, and you see the dark spot. What do you think that dark spot represents? Yeah? Lack of ink. The negative space. So the network is not only learning where the ink should be, but it's also learning where there should be no ink, the negative space. It's very interesting because, a lot of these networks around vision, like, cat, dog, bird, boat, shadows became an important part of the recognition, which I think was part of the breakthrough. Okay, so we see 3. You can kind of see probably in the back the ghostly shape of the 3. Right, that is what the average 3 across 60,000 inputs looks like. Then this layer does something that is where the magic is really. Right? I think your question was really around why do we need this layer? Wouldn't that be enough? And what this layer is doing is it's saying, well, there's probably some elements of 3 that reflect not 9 or not 0 or some weight of 7. Right? So we're taking those primary features from that first layer and seeing whether there's some residual information that we can put together to really amplify the predictiveness. We see it here on 7. I like 7 in the sense that there's a lot of darkness in 7. Right? 7 is saying, hey, okay, we've got the 7 feature, and it's going to put a bright spot here. Don't look for bright spots anywhere else. Okay? So, questions? Yes?
Things say that the first layer is looking at is like an initial pass of just what are some features of 0 through 9, and then the second pass looks at what it's already learned of 0 through 9 to figure out essentially the differences in what it's learned to see. Instead of just taking the raw inputs of, well, I've already figured out the features of 0 through 9. Now let's figure out the probabilities of those features to see, oh, well, if it's more like a 3 and an 8, then it's definitely not 7.
Kind of, yeah, you're getting the right spirit of it. It's combining these things we learned from the first layer in a way that improves the accuracy, right? That's kind of a bland way of saying it, but yeah. Yeah, we could add another layer, third layer. But probably we've squeezed out all the information with these first 2 layers. So it might add some accuracy, but what we'd find is the filters look, they all kind of look the same. There's not as much differentiation there. Okay, I really need to get to the punchline, which is here. Multi-layer perceptrons, backpropagation, we're now in the early 90s. That's kind of where we are in history. Okay. But we hit this problem very quickly, that if we want to scale the world, we're stuck, right? We've got 28 by 28 image, 784 pixels, and we've got this network, 8,000 parameters. But what if the images were 250 by 250? Right? You can't find cat, bird, dog, boat on 784 pixels. You need a bigger image. So let's say the image is 250 by 250, which is still very small by today's standards. Well, if we were to use a multi-layer perceptron, we end up having 4 billion parameters. You just crunch through all the math. There's no way in the 1990s that you're going to be able to solve a problem with 4 billion parameters. So we're stuck. And the breakthrough happened. The idea was, well, let's use this idea of a convolution. Let's put a convolution into the mix. Why convolution? Well, these people in image processing are already using convolution as a way to represent image features. Right? Remember, a few lectures back, I put up a convolution that helped us find a straight line through an image. So we're already using convolutions to do these. Can we put them into a deep network? That's the question. And the answer is yes, and I'm just going to flip through a bunch of slides here. And we end up here. Okay, this was, I would say, one of the first, probably the first, convolutional neural network. And at this point, we're starting to get deep. It's not just 1 or 2 layers, but this looks pretty complicated. And what we're introducing now is a convolutional feature map into this big mix. What it does is it lets the network become much more complex, taking larger inputs. In the case of LeNet 5, from Yann LeCun, who is still one of the luminaries in computer, in machine learning, deep learning. This is something he proposed in the early 90s. 32 by 32 inputs to do very, very accurate, I think, handwriting recognition. So it's not just digits, but it's handwriting of all kinds. Okay, we're going to stop here today. When we pick it up, we're going to dive deep into the computation of this, because that's what your project is based on.